In this short tutorial, I will show how to quickly prepare a special quasi-random structure for certain BCC high-entropy alloy using ATAT mcsqs module with input files generated by SimplySQS interactive online interface. So let's start. So first you need to navigate to this website, or you can just simply write simplysqs.com and it will redirect you here. And then you need to upload your initial crystal structure, like the initial BCC phase, which will define the initial atomic positions and initial lattice parameters. So in my case, I will use beta titanium, and either I can already upload here the zip file, or I can search for it in this implemented database search. So let me search for the BCC of beta titanium. And this should be quick. Yeah, so then I can browse through the structure and select which I want to use as input. So for instance, I will use this zip file from COD database, and now I can either download the zip and then put it into this interface, or directly add it into the application with this button. So for me, it's better to download the zip with this button and then simply upload it here. So in case I need to use it more frequently, or I could also add the structure just with this, but then I would need to research it again. Okay, so once I have this zip file here, I will close this search. I can preview the structure, and now I can define like what should be my supercell size, or the number of atoms that the resulted SQS should have. So for instance, I will use 4 times 4 times 4 supercell, or 128 atoms. And then I need to already specify what should be the elements that I want to have in the SQS and their occupancies, or this at this initial at the atomic positions. So let's, for example, let's say I want to have here zirconium, titanium, niobium, and aluminium, and then I can specify the concentrations. For instance, 40% of zirconium, 20% of titanium, and let's say 13% of niobium and 25% of aluminium. Okay, so this defines the structure, and then the parameters for ATAT mcsqs. So the main ones are the pair cutoff distances, and if I want to include also triplets or quadruplets, so for example I will include triplets in my SQS search, and I will include pair cutoff distances up to, let's say, third nearest neighbor. So yeah, this 1.5 angstrom parameter is fine, and these parameters are calculated like from the normalized unit cells. Like the lattice is divided by the maximum lattice, the initial maximum lattice parameter, so I can like more directly see what is the distance between first nearest neighbor, second nearest neighbor, and etc. And for triplets, I will include up to second nearest neighbor, which is this value is fine. And now I can generate the ATAT input files. So I have now two options. Either I will create these two input files and put into them their content, or just download them here and then run the search with these commands, or I can skip this and use one universal bash script that will perform all these steps for me. So I will use this second option, and in this second option I need to specify if I want to search for a specific supercell size or for like specific numbers of atoms where the lattice like this the structure parameters will change. So I will use for supercell size fixed, and I will enable parallel execution. So I will search parallelly for 5 best SQS structures, and I will not set any time limit. I will stop the script of SQS search myself. And yeah, now I can generate the bash script, and then I can either download it here or I can see the content here and copy it to clipboard. And this is what I will use, or what I will run for the ATAT mcsqs search. Okay, so now I will go to console where my ATAT is compiled. Let me clear this previous testing. I will remove everything, so it's empty. And first you should check if you are not sure if you compiled ATAT correctly. If you write this, it will show you these options. So you have to set the like the path to the ATAT into your environment path variables. So that I did, and yeah, I have this command. And then because this script also automatically converts the best SQS structure into postcard format, which I can use for VASP simulations, or I can directly visualize the structure in, for example, Vito. Then you just need to have a NumPy Python package, but that's pretty basic one, so you probably already have it, or you can just install it if you write this command. Yeah, and just you either create virtual environment, or you can install it across the system with this. But I probably should have it already. Well, anyway, I have it, and so let me run the search. So I copy the content of this, and then I will create the bash script, call it like this, for example, and insert here the content, and then save this with Ctrl+S and close it Ctrl+X. So I have here the script, and I can run it like this. So this will take a little bit to initialize the console, but the run already started, and in the console it will be updated every minute, and it will show you like what is currently the best objective function value and from which run it is. But if I go to the folder, you can already see the outputs from this run, which are gradually updated, and I can then visualize in this interface like how the convergence of the objective function look like. So for instance, if I copy here all these log files from parallel runs, it will show me how the objective function is changing for each parallel run. With like this is updated when it found a better objective function. So here there is no time dependence, but if I want to see like how the objective function is changing over time, then I can upload here this file, and it will show me how it's changing with the search time, the objective function, and also directly I can see like currently which run has the best objective function and which one has the worst objective function. And yeah, now I can leave it running for like several hours, or like when I will be satisfied with the convergence, I will see that nothing is changing in the objective function for some time. Or just to illustrate you that it will automatically create the postcard, I will now stop it with Ctrl+C, and once it is stopped, it converted each best SQS into this format. So now if I refresh this folder, I see here the postcard files, so I can directly use them for some other simulation, for some simulations, or I can visualize the structure itself. And here I created the special quasi-random structure for my example of some high entropy alloy. Okay, so that is all, and thank you for your attention.